For example, let us look at a very simple example here. Let's look at a counter, right? We started with, I told you that a state machine in the first class, right? The most common state machine that we encounter in real life is the traffic signal, right? There is a signal counter that is counting 0, 1, 2, 3 at a frequency of 1 hertz, right? It's counting at 1 hertz because every second it is changing, right? In fact, it counts down actually, it doesn't count up, okay? But the point is, let us say I want to design such a counter, right? So what is the idea here? The idea is actually you take the previous state and simply add 1 to it, right? That's the whole idea here. So what do I need? So let me consider a 4-bit counter. I'm going to consider a simple 4-bit counter, okay? And what I'm going to do is, I'm going to put a full adder here, right? And if I were to now design this counter, I want to see what I need to do to design this. Full adder, full adder. Right? So this is A, okay, I am giving the A, B inputs like this, A1, B1, A2, B2, A3 and B3, right? And I am going to now propagate the carry out like this, okay, I am propagating the carry out downwards, right? And what I get here is my sum bit, S0, S1, S2, S3, okay. So now what is the general idea? I want to add 1 to some number. Actually that's all it is. If you give me the current state somehow, I am going to add 1 to this. So what do I need to do? I am saying that my numbers, by the way, A3 to A0 is, this is the MSB, okay. Likewise B3 to B0, right? Exactly, perfect, right? So this is my MSB, and therefore if I want to add 1 to this, what should I do? I just need to make my B3 down to B0 as 0, 0, 0, 1, right? So all I'm going to do is I'm going to tie this to 0, one, right? So whatever the value A is, A0, A1, A2, A3, I am just going to add 1 to that particular number, okay. So if my A3 to A0 happens to be 0, 0, 0, I will add 1 and I will get 0, 0, 0, 1 as my output state, okay. Now if my input itself was 0, 0, 0, 1, I will add 1 to this, 1 plus 1, I'll get 0, 1, 0, 0, right? Effectively, you just add 1 and the next state is automatically available at the output of this adder, right? The question now is, how do I take this state, the previous state, and give it back as an input to this system, right? So that is where the main problem is, right? And that is where combinational block cannot solve this problem for us, okay. So let us see what we can do with this first of all, okay. And just to sort of give you a feel, right, if I just take this system and call it a combinational block, I am talking of, I'm going to look at a system which is like this, A3, A3, A2, A1, A0, and then my output S3, S2, S1, S0, right? Or maybe I should just write it in the same order that I have written here, A0, A1, A2, A3, and S0, S1, S2 and S3, right? So this is basically my combinational block. Okay. Now you will also see what I mean, by this timing diagram, this in between transitions and all that stuff. Okay. So if my input was 0 0 0 0, okay, the A input, okay, the output has to be 0 0 0 1. Now if my input is 0 0 0 1, output will be 0 0 1 0, right? Now if I go from and if my input likewise is 1 1 1 1, then I want the output to be 0 0 0 0. So what will happen is, the moment A0, A1, A2, A3 arrive, the output of full adder 0 will be ready first, okay, because its carry is now going to propagate to full adder 1. We saw this was the ripple adder property, right? So S0 will be available immediately. So if I go from 0 0 0 0, right, if I go from this state of my input, right, this is my A3, A2, A1, A0, S3, S2, S1, S0. If I go from this state to 1 1 1 1, then obviously what is going to happen is, my S0 will settle first. Okay, so let us now understand, what this particular timing diagram actually meant. Okay, when I said that you go through some intermediate transitions, right? Let me just give you a physical feel for that as well. So let us assume that my input A3 to A0 is going from the state 0 0 0 0, okay, which means my sum S3 to S0 is going to be 0 0 0 1, corresponding to this input state, okay. And let's say this is my state, this is state 1, state 2 is 1 1 1 0, okay. And what do I want it to do? Let's say I want this to go, or I'll say something even better. I will say 1 1 0 1, okay. That means I want this output to go to 1 1 1 0. If I add 1 to 1 1 0 1, the sum output eventually should stabilize to 1 1 1 0, right? Now let us look at how I am plotting this, okay. So I told you that the primary inputs, which in this case was A3 to A0, okay, is going from state 1, that is state 1 equal to 0 0 0 0, to state 2 which is equal to 1 1 0 1, okay. And I am going to look at the primary output S3 to S0, okay, here. Remember, I told you that after the input changes, you will have some random transitions like this, and eventually it will settle to its actual state. So the state 1 corresponds to 0 0 0 1, and state 2 corresponds to 1 1 1 0. Okay, now I am going to look at what are the states that S3 to S0 go through in the process of going from 0 0 0 1 to 1 1 1 0. Okay, so now what happens is, just think of what happens. The input A0, A1, A2, A3 changes from all zeros to 1 1 0 1. Okay, so I'll put that in magenta. Originally everything was 0 0 0 0, everything went to the new state, which is 1. Okay, so 1 1 0 1, yes, right. So I am going to now look at what happens through this ripple adder, okay, in the process of the input going from 0 0 0 0 to 1 1 0 1, right. So when I see this new one coming here to this full adder, okay, the full adder will add that 1 with the other 1 which is sitting here, right, and produce a sum which is 0. So if I look at what was my corresponding output here, right, for S0 S1, it was initially 1 0 0 0, okay, and then this 1 will become its actual value 0, the first in the after the first full adder evaluates, okay. But now what have I done? I have basically taken, let me do the addition here and show you, 1 1 0 1 plus 1, okay, I add, I get 0, I get a carry here, right. So the carry now gets generated here, okay. So now the carry gets added with the input A1 equal to 0 and the other B1 equal to 0, that is already 0, and this will then become 1, right. Now what do? I add 1 plus 0, I get 1 as the answer, there is no carry, okay. And now if there is no carry, then actually A2 and A2 arrived at t equal to T1 itself at this instant, T1, right. So this would have changed to the output, 1 plus 0, you will get 1 directly here, right. There is no carry here to be added, therefore 0 to 1 would have happened along with this 0 here. These two would have happened together, okay. And of course now what is happening? I have 1 plus 0 and then I have 0 plus 1, I get the answer as 1 and then 1 as the answer. So what would have happened in this case is this S0, S2, S3 going from 0 to or toggling its state would have happened after in one full adder delay itself. This would have happened in 2 full adder delays. So if I look at this state here, the way it would have transitioned before it went to its steady state value is this would have gone through 2 transitions, right. If I just blow this up a little bit, it would have gone through 2 transitions like this. What is the transition? After one full adder delay, okay, after one full adder delay, it would have already become what? The 1 would have become 0, so it would have become 1 1 0 1, okay. And then the second full adder delay, after another full adder delay, it would have become 1 1 1 0, I am sorry, because this one would have happened after one full adder delay, and then it would have become 1 1 1 0. So this bit takes 2 full adder delays to actually get ready. Of course, the worst case is when the carry propagates all through and the delay actually takes that's the longest delay, right. But I am just trying to say that when we draw such a thing, it means that the outputs, at least one bit is changing, or the output or input, whatever those set of bits are, at least one bit is changing, but we do not know what they are, we don't care what that intermediate state is. Eventually it will come and settle to its final value, which is 1 1 1 0, okay. So this is just to keep in mind what actually happens because of these delays and how the circuit actually propagates these delays, right? But in general, we will not worry about this intermediate state. I just gave you a concrete example to show you why it goes through these intermediate states, okay? So now let's come back to our problem at hand, which is basically the case of designing the counter, okay? So we have a combinational block that if I now, give the sort of the current state, it will add a 1 and give me the next state, that is known. But how do I take the current state and give it back, right? So that is the main problem that we are trying to deal with, okay? So let us look at that. So I want to see how I can achieve that. So let us not look at all these states for now. So what I actually want to do is, technically, if I can feed back like this. Technically, this is what I want to do, right? This is what I actually want to do. I want to take the sum output, right, which is actually the next state, and feed it back as input to this state so that it can be used to evaluate the next state, right? So this is what I eventually want to do. So let us see what the problem is with this kind of a system, okay? So we already know that, okay, so let's say somehow I have been able to reset this A0, A1, A2, A3 to some 0, 0, 0, 0 initially. Okay, somehow I have been able to do that. I'll tell you how to do it also later. For now, let's assume that the initial state is 0, 0, 0, 0. Then what will happen after a propagation delay, right? After a propagation delay, right? So you look at this. If I now look at, of course, S0, S1, S2, S3 is the same as A0, A1, A2, A3 because I have just fed it back now. So, okay. So, if I look at S3 to S0, right, what will happen? Here, I am going to give, I somehow start with 0, 0, 0, 0, okay, and therefore my S0, S1, S2, S3 starts with this state, right. Now, after a certain propagation delay, right, what will happen? My output is supposed to change, but we also know that the output will start changing, to some transient values. So S0, for example, will now quickly change to 1. So this S0 will try to go to 1. Okay, S1, S2, S3 have not yet settled to its final value because you have to propagate the carry, you have to do something there. They have not yet settled to the final value, and therefore you will go to this new state which is 0, 0. This is what will happen. It will go 0, 0, 0, 1, right? Now this S0 has reached a new state and it will be fed back again to its A0, right? Automatically that full adder will evaluate and give you its new value, right? S1, which is supposed to go to 0, 0, 1, 0, right, will not have enough time because the full adder 0 is actually continuously evaluating, because of this feedback. Okay, so there is sort of a race condition that is happening on that full adder right away, right? And therefore, if you look at if you just observe the state, right, it will be impossible to actually pin down that state to any particular value. It will just continue to be in this, I would say, this transition period always. There's no time. Yes, it may go through, somewhere here it may go through 0, 0, 0, 1, right? Or here it may go through 0, 0, 0, 2, 0, 0, 1, 0, and so on. But it cannot remain in that state even for a deterministic amount of time, right? So there is no way that we can actually make this system. And how fast will this change? This will change literally at the speed at which these full adders change its output, Okay. So therefore, what is important now is I not only need to be able to feed back this, current state to the input somehow, but I also need to be able to feed it at the frequency at which I want the system to actually work. In some sense, I want to control the time. Okay, I need to control when the state changes at these A's, and therefore it is not okay to simply feed back the output just like that, right? Now you could argue that I could just add delays here. For example, instead of just feeding back, I will add like, okay, this two inverters is basically a buffer. Okay, logically there's no inversion happening. If I put two inverters, back to back inverter, and I'll put an even number of buffers, large number of buffers for everything, right? But again, what happens is each S0, S1, S2, S3, they are all going to react. They are all going to give you outputs at different times, right? Because of how the ripple adder is working, right? And therefore, it is not possible to get the state of S0, S1, S2, S3 back to A0, A1, A2, A3 consistently at the same time. Okay, so the primary requirement is one, I need to control the delay, how much time I want to give it back, when I want to give it back, and I want the state S0, S1, S2, S3 to be available to A0, A1, A2, A3 together. I don't want it to come at their own speeds and delays. Otherwise, what will happen is this S0, S1, S2, S3, if you look at it, it will be always in some random transition mode, okay, and therefore that's not going to be useful. So in some sense, what I want to do is, I want to take this combinational block, okay, which has some inputs like this, okay, some outputs like this. I want to introduce delay, okay, and I am going to feed these primary outputs back like this, right? Okay, and I could have equal number, I mean this, for example, I could have two inputs which are not being fed back through this system, but they are just primary inputs, okay. So these are primary inputs, okay, and I could have one output again which is not, primary output, right. This is my current state, and after a delay I want to give it to as what I call as next state, okay. But remember, this delay, I want it to, first of all, I should have control over it, right. If I just put a bunch of inverters like this, then I cannot control the delay after the chip has come back, right. Whatever delay I get, right. But imagine your signal counter, I may want to make it count at 1 hertz for the signal, but elsewhere I may want to program it so that I can count at 2 hertz, 100 hertz, 1 kilohertz, it doesn't matter, right. Effectively, I want that guy to count very similar thing, I want to make it happen, but at different frequencies. Therefore, I need control over frequency. I need to control the frequency somehow, right. And most importantly, this primary output, will go through these changes and eventually settle to its final value. These outputs, my current state, right. When the input changes, it takes some time, it will go through these transitions. I want this final state to be made available to the input, but all of them together at the same time. Okay, so I want to ignore these transitions somehow. That's the key idea that I want to implement, and we are going to see how we can implement that. Okay, so first of all, in order to implement such a sequential circuit, right, and therefore, by the way, this is what we call a sequential circuit, right, or a state machine, finite state machine, right. The system is going through a finite set of states, and the next state is a function of the current state. Okay, so what we are basically saying in this counter case, it is very simple. The next state is current state plus 1. You could have any other combinational block instead of a full adder, ripple adder there. You could put any combinational block. You can take the current state, you could take the current state, feed it back, and then sort of get the next state. Okay, so that's the basic idea here, right?